Lights.
There it is.
There you go.
What was that?
I know. Magic day.
Okay. All right. So we're going to go over the rest of what we're going to cover for TCP with the exception of congestion control. We will go into that next, and then that will wrap up the transport layer, and then we'll get on to the miscellaneous topics. So.
We're going to cover security, right?
Huh?
Security.
Oh yeah, we're covering security.
You had a chance to like outline what you want from that critique paper, so we can get going on that?
Yeah, so the critique paper, generally in a conference paper, and I encourage you to do it this way, is a conference paper. It has like an introduction, and then motivation. And then following motivation is the actual real meat
Oh
of it.
yeah, like I've written some papers before, but I'm saying like what kind of questions you want us to kind of hit on for answering that.
So the critique of the paper would be, and granted, some of these papers are really good, right?
Right,
So it's
right.
not like you're going to find giant holes in
Right.
them. But remember, it's not a. When I say critique, doesn't mean you have to find a hole in it. You also could look for, hey, how could I take this paper, which is really, really good, and build on it to do something else, right? Can I pivot with the information in this paper, can I pivot to something else? If I took it, it was demonstrated in this particular field or topic, can I apply that same logic to a different topic and come up with another unique result? When I say critique, that's what I'm saying, right? It's a critique as in you received a paper in a conference, and you are telling the author what you thought about this paper.
So, did you check my format yet?
I have not checked your format yet. Sorry. I will get to you. I wouldn't be super worried about the format because I would suggest that you put it in IEEE or ACM or one of the other formats and just get used to that. All right. So, we have data we're sending from one host to the other host. Right? And we decided that, hey, we could come up with a mechanism with sliding windows so that we could fill up our network. Right?
And we're talking about TCP here, right?
We're talking about TCP, yes. So, or in the context of TCP. That's just the easiest way. So in this thing, we have some sliding window, right? That we call W. And we figured out, hey, how you fill up the network is you need twice as many windows as the bandwidth delay between the two computers, so that you can fill up the network in both directions. Obviously, the windows are divided on however big your packet size is, right? And then you can fill up the network. The problem is, we look at one of these routers, it has a lot of incoming connections. Ours is just one of them, right? It has a lot of outgoing connections. We could have many different computers going through the fabric, right? And pushing out the same connection. Right? HBO Go when Game of Thrones comes out. Right? And so now we have one connection, and there are ways that we could put our data in different places and blah, 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 but there also needs to be a way for the network to be able to handle this. Right? Because if you look at this from a different logical view, the same router, right, you can envision it as having a buffer for every outgoing port. That's not exactly true, but you can envision it as that. Right? And this is our HBO Go port. Well, there's only so much data that can be shoved down that pipe. Right? So eventually, our thing is going to get full.
Excuse me.
Yeah.
So that's the router buffer. Is that like for one user, or is that for multiple users? Because that's like it's dense.
Well, it could be for one user, because you could have a fast network on one side and a slow network on the other.
Mm-hmm.
Right? So inside of here, this network, right, when this thing starts to fill up, this is congestion. Right? We've talked about something like this already. But it can also happen on the hosts. We have buffers on the host. So we have a buffer, and inside of this buffer, we only keep track of the current window. So we have negotiated this window, we only keep track of that. And so this is a circular buffer, and we just keep going around and around and around it. So what happens if we start filling this thing up? This is very similar to congestion, but it's not, because it's really happening on the host. It's not a network issue. So as this thing starts filling up, we have our, let's just do it this way. We have ACT stuff in the back, right? Future space here. Don't really need this, but it helps us visualize it, right? We have ACT stuff in the back, future space here, and then we have our, well, this would be it right here. Our last ACT pointer. And so what we do is, as we take this stuff off and pass it to the application layer, right, we simply move this pointer. We don't do anything with this data, right? We just move the pointer. It's our computer science form of delete, right? We move the pointer, and thus is dead to us until the pointer shows up again, but that's fine because it will be overwritten by the time the pointer shows up again. The problem is we only have this window, and this window is shifting over one of these buffer spaces every time we have an ACK, which allows us to put another, if we shift it over you know, with our ACK here, we get another ACK, then we shift it over here. And we shift this window, we can keep track of it that way. The problem is we can never let this window get full. In reality, the window isn't tiny like 5, right? It's much bigger. Like somewhere in K, right? Somewhere in thousands of bytes.
Is that what the ACK stands for, the LA?
Huh? No, that's our last ACK.
Oh, last ACK, okay.
Yeah.
So you move it to the application there.
Yeah, and so when we ACK, we simply, in the buffer, we don't actually delete any data or anything, we just simply move the pointer over one spot. So the question is, how do we keep this window from filling up?
Well, we can set like a window size 0, meaning that just like slow down.
Correct. So what if in our ACK, we actually tell the sending program how many windows we have left? So if we look at our model, right? We're sending here and we're ACKing here, right? If we're sending and ACKing anyway, why don't, when we ACK, we tell the sending program how many windows we have left? So in this case, let's say we have 2, so I got slashes over here for ACKs, and let's have wavy lines for non-ACKs, and then let's have empties for empties. So I have 2 empties. When I receive this packet, we ACK it, and we ACK it with a window size of 2. Now, we're still in stop and wait, right? Because then he would send a 2, right? And then presumably our thing takes data off, but maybe it doesn't. So remember, this is asynchronous communication. When it arrives at the application may not have called receive yet. And so if it hasn't called receive yet, all this stuff is in the buffer. And so there may come a time where we ACK and we send a window of 0. That tells the sending the sending computer to stop sending me stuff. I am full. Well, then what do we do when we're not full?
Send them more.
We send another ACK with a window, however big it is, right? Let's say it's 2. And then they will send stuff again.
So how do they agree upon an initial window size? Is it the size of the receiver responsibility?
Huh?
An initial window size.
So that's a really good question. I don't know if that's done in connection. It probably is done in connection. There's a window in the TCP window whole field in the TCP header, and so it probably has that.
Well, it does that during the 3-way handshake, I guess.
Yeah, that's what in the connection. Yeah, so like the last.
That's the maximum window size.
Yeah, it would be because you haven't sent any data yet.
Yes.
Yeah. So if your buffer's empty, then you would send the maximum window size.
So if like the receiver sends the ACK with like, I have 2 slots open, does the sender just send 2 and then wait for another ACK even though like the window is larger?
So let's talk. So right now we're just going to stop and wait. We will get into like when we're filling it up, right?
Okay, yeah.
Right. So because it becomes much more complicated because now we have we're going to have ACKs with multiple windows, by the way. Right. So you'll have an ACK with, hey, I got this 100 windows, and then you can have 3 more ranges after that to say that you can put stuff in that I've received this other data that is not in sequence. So I mean, it gets much more complicated. Let's stick to the easy parts first.
Okay.
So we can simply act when stuff calls up. So recognize that these buffers stay full until you call receive. Until the application on this side calls receive, that buffer is there. And so when it calls receive, then it can take it off. Also recognize that this can be, we are talking as if these windows were static sized, right? They're not, right? So this particular computer can be sending 1K data packets for whatever reason, and this particular computer can be pulling 2K off of out of the buffers in one call. Because these buffers, all of the is passed up to the transport layer, and so everything has been stripped off. There's no more control information in it. And so there's some logic that we've read, and we can look at like a state machine of where we are in our control logic, right? But inside of this data, it's all gone. It is simply whatever the app is expecting as a byte stream. So if we have a byte stream over here, and we break this up into 1K chunks that TCP sends, then over here, receive can pull those off and stick them in there, and those message boundaries don't exist anymore once they're in the buffer. So when I say, let's say each of these blocks is 1K, right? It's not, it's all 1 byte. But so if I pull off 2, then those become gone, and really the only thing that we do is move the last act. And we send the act, obviously.
So you're saying once it's received, the buffer will not exist anymore, and
Well, so the
message is
receive
back.
can pull some of the buffer off.
Okay.
It can pull all of the buffer off. It can go check the buffer and nothing will be there, and so it's blocked.
So the
Right.
message is inside of it.
So when you call receive, part of what you get is in return is how many bytes were taken off, right? So like, let's say you call receive and I want 4K, but it's possible that even though you wanted 4K, there was only 2K there, right? So you get 2K back. So you get like a byte's read.
So, one quick question.
Mhm.
I'm not on TCP. So in case of UDP, like for the project, does it matter how much size we're chunking it into while we call the particular file? Since we have like a 40, like a 4K.
For the project, it wouldn't really matter unless you were trying to stick too much data, because UDP,
It sends everything.
it just sends, right?
Okay.
And UDP by itself, unless you're building logic on top of that with the application, UDP by itself just fires and forgets, right? Bullets left the barrel, and it lands where it lands. You think you know where it's gonna land because that's where you aimed it, but sometimes it doesn't make it there. Right? Sometimes things go wrong. So, instead of our 1, 2s, and 3s, let's look at something that's a little more real life.
Still using stubborn weight?
Yes.
Okay.
Yes. Just a little more real life.
Yeah, that's okay.
All right. So this is going to be our sender. This is going to be our receiver. And so we, and try to keep it at least a little simple numbers. All right, so let's say that we send 2K of data across with sequence equals 0. Then, and let's say that our buffer over here is 4K. So we send 2K of data across with sequence 0. Then what do we act with?
2001.
So we act with,
Okay.
I guess we keep the numbers kind of simple. So we act with
2.1. 2.1.
2.1.
Well, it's gonna be much easier to keep it with bits. So,
Yeah.
if it's 2000, then it's gonna act with 2001, meaning that I received all 2000.
Yeah, it's gonna act with 2001. So let's do act 2001. My example is like 2Ks and 2048. But so 2001. And what else do we send with it?
When,
Sequence
2K.
one.
When 2K, right? What's the when 2K stand for?
Left space of 2K.
Yeah, yeah. So then we send another 2K data. And what's our sequence?
When 0.
Huh?
Not sequence, not sure.
We send it with sequence 2001. Right? And let's say, as of this point, receive hasn't been called yet, and so we're full. Right? So what do we send back? So act, in this context, we're gonna do 4001, right?
Yep.
And our win is what?
0.
0. And we quit sending because we gotta win 0. And then there's something happens in here, receive is called, and it takes off 2K. Right? At that point, we send another ACK. And the ACK is what?
4001.
4001.
And whatever the size that is available.
2K, right? If we took 2K.
Oh,
off.
okay, 2K.
Is there a way for the sender to know that this is a duplicate ACK?
Sequence.
Yeah, the sequence number. The sequence number is the same, so it knows that, hey, this is just an update on the window size. Now to just clarify, we have a 4K buffer, right? We could continue this on. I'm running out of space here, but. Right, what if we sent 2K again? And what's our sequence number?
4001.
4001. What's our ACK?
6001.
6001. And I point that out, just because we have a 4K buffer, internally we are looping that, doesn't mean that we're looping our sequence numbers yet.
I have a question.
Huh?
So when it gets to 6001, does it not mean that it increases 2K over the maximum limit that it might receive?
No, because we chunked out 2K here, and so this thing's only half full again,
Okay.
right? And so our sequence number is 6001, right? But that doesn't necessarily reflect our pointer inside of here. Our pointers simply cycle over 4000, but the sequence doesn't, because we will simply use the entire sequence size in the TCP header, and then we'll cycle that over. So now we can at least keep track of stop and wait, right, with window sizes. The next thing we need to figure out how to do is figure out how to set our timeouts. So when we were talking in the case of like a single Ethernet switch, right? The timeouts are very easily determined because it's the width of your network, right? Maybe a little tiny bit of switching delay, right? But they're pretty easy to figure out. Not so easy to figure out when you're crossing the entire internet. So when you're crossing the entire internet, now we have some serious issues because we're not even sure what the networks are in the middle. So if we're not sure what the networks are in the middle, we can't use simple math like, oh, well, you know, this is Ethernet and it's, was it 323 feet or whatever the exact, you know, and then we can figure out precisely at, you know, 2.3 times the speed of light what our propagation delay is and blah, 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 and we can figure out a timeout and make it really, really precise, right? So now we need some way to come up with a fuzzy timeout. Something that's not too big and not too small. Why do we want something that's not too small? That was the easy question.
So we don't time out when still like just coming to it.
Yeah, well, so like this is the natural path through the internet is as fast as it can go. If it was too small, nothing, it would always time out, right? And why don't we want it too high?
Packets from the 70s aren't still bouncing around.
Correct, right? So you don't have drop packets from the 70s still bouncing around, right? Those are time to lives. But the idea is the same. Is if we have to wait for an acknowledgement, right? We don't want to wait forever for that acknowledgement to come. At some point, we need to assume it's not coming. The problem is not only is our network variable, but the traffic inside it is also variable. Remember, we have congestion, and sometimes that congestion will build up queues. And as queues are building up, they're not being sent across the network. And so if we're all going to HBO Go to get Game of Thrones, then the delay inside the network is going to be longer because the queues are and the routers are filling up. And so we'll have something that looks like this, right? And then HBO Go, right? So if these are our average delays across the network, right? Our delay is never zero because there is some physical property that says we can only get across the network so fast, right? That's our bandwidth delay. Speed of light is constant, it can't go any faster, and it's slower even in some mediums, so somewhere down here is our bandwidth delay, right? Probably should draw it a little better. It should touch probably some places here, right? Where the network is seriously optimal, right? We also need some way to get up here, and so what we want is some way to stick in this range and have something that looks very similar to this.
So can we say that the minimum or the lower bound of the what was it again? Sorry, the lower bound of the delay is at least the round trip time.
The lower, well, the bandwidth delay product.
Yeah.
The lower bound is at least the bandwidth delay product, plus switching time.
Common filter.
Huh?
A common filter is state estimation.
All right.
Here you go. Smooth the data.
We can smooth out the data, and that's exactly what we're going to do. Is what's an easy, mathematically simple because we have to calculate these things continuously, remember, we're running into some serious problems, right? The entire network is distributed, right? Nobody's in control, right? Right now, we are trying to figure out just the host, and then in congestion control, we'll figure out the network part. But there's billions of hosts on the internet, right? And there are billions of hosts, they all need to be able to calculate independently what their best timeout value is for talking to this computer at this time, which will change, right? Because Game of Thrones is coming on. And so it's going to change. So now we need an algorithm that each host can calculate independently, continuously, such that we can figure out the right timeout.
Plus or minus 2 standard deviation.
It's actually
Or
plus,
variance?
plus or minus 4 standard deviations.
Oh,
We're actually, so
wow.
it's actually plus 4 deviations. So what we can do is we can measure what we are at currently, right? And so the current currently we could estimate, like, this is where we're at current, let's call this is what we were at last measurement, last final measurement, right? And then we can say, hey, this is what I just measured. And then we can do simple math and say, I want 90% of this and 10% of this. So just by doing that, right, we'll be able to flatten out our curve, but it won't rise fast enough, right? So if you recognize 90% of this and 10% of this, that means that if it rises sharply right here, right, this curve will be too slow. So what we do is we just take 4 times this, 10%. If we take 4 times that, and by the way, this is the current measure here, like the actual delay time, right? And this 10% that we're taking is the rate of change. It's not the actual 10% of what we're currently, it's the rate of change. So that is the slope of these lines, right? And so if we have what we have currently, if we take our graph, right, this 90%, this graph looks something like this.
It's kind of like PID or something.
Huh?
Kind of like feedback.
Yeah, because you're taking an average, right, as it's going across. But it's a sliding average. And then we have the rate of change, which will look something like that, and then we add them together. Except for we take the amplitude of this 4 times and add it together. And it turns out that actually super easy to calculate. It rises very quickly and slowly lowers. Right, so there is some inefficiencies here, but there's better. Why would we want inefficiencies here and not here? If we have an inefficiency on this side, if we didn't take the rate of change, right, and we rose too slowly.
It's like losing everything because we're timing out like every packet.
Yeah, so we're timing out for every packet, which is also causing retransmissions, right? Which is adding more packets into the network, which is causing more problems, right? So we would rather we'd rather put the burden on the host on ramping down too slowly than the burden in the network of filling it up. So if we ramp down slowly, that just means that these guys are slow for some, and this is going across, I mean, this like represents like 10 seconds, right? So it's not like it's slow for a long time.
So one question. So
Yeah.
when does this really happen? Is it for every packet that is being sent? Or it only
Yes.
happens for the first packet?
So every packet that's being sent. So when you do your head shake, you can figure out how long it takes to traverse the network. You can get a base value, right? The next packet, when you get the ACK for that packet, you can figure out how long it took to traverse the network. You get your second value, right? And it just continues on and on. You keep applying this over and over and over again.
So that means when the first packet is being sent and a hack is being received, we already have a base value, right?
Correct.
And we use that base value to calculate the next one.
Yeah.
Like how long it's supposed
Mhm.
to take to receive an hack.
Yeah.
Oh. Okay.
And this is actually how it's implemented in TCP. And it's really nice and convenient because 4 is a very convenient number. In binary, how do you multiply by 4?
Left shift.
Yeah, left shift twice. Right? It takes 1 clock to do that. Right? So when you wonder why all these numbers come out in weird multiples of 2s, because somebody decided it's easy math, right, for a computer. And we need to be able to do that quickly. It's not a big deal anymore. Our hosts, right? Even if your host is a phone, it's many times as powerful as computers were 10 years ago, right? So, but this is why we just shift left twice.
So the titles on this would be response or delay time? or-
So all this is doing is trying to measure the delay time across the network so that we can set in our right, we're trying to set this timeout value. So if I don't get an ACK by this time, right, I need to retransmit.
I was just asking for titles on the graph too, for later when I look at it offline and probably.
Oh, yeah. So I've been writing over the top of it over and over again. But what we're really trying to do is we're trying to smooth out the graph.
Yeah.
We're trying to rise very quickly. And because we are rising very quickly, we sacrifice that sharp rise with a slow descent. Slower descent. But it's not bad. And that way, because the worst thing that can happen is there is a packet that you should be receiving, and it's just they're slow. And because then you add another packet to the network. This is like this in the first place because we added a packet to the network.
Yeah, I wanted to ask you another question about the graph.
Uh-huh.
So you said that the 90% of it will smooth it and will make it to the bottom part of the graph. Then what about the other graph that you drew at the
So
bottom?
what we're taking is 90% of the current value, and we're adding 4 times the rate of change.
10% of the
Yeah,
bottom.
four times 10% the rate of change, right? So that what we do is that it causes it to rise very sharply when, if you have a graph that looks like, right, and then you have something like that, right? The slope on this thing is very steep and the amplitude is very high, right? So there's a giant rate of change. Very interesting, a PhD student made a paper on this, and they were able to detect, so one of the, if you look at some of these graphs, they look very similar to brain waves, right? And if you look at an epileptic seizure, the brain waves are,
Network congestion.
yeah, it's basically network congestion. So it's, it sounds funny, but it's kind of what it is, right? It's network congestion, and they were able to detect epileptic seizures instead of measuring the amplitude of the brain waves, which everybody tried before. They measure the rate of change, which is exactly what TCP does. He's probably PhD out of that. Another idea gone. All right. So, we're gonna get out early today.
One quick. I'm sorry, I keep going back to the same thing. So what if the rate of change is more than 4 times the 10% that we're taking out? It has to retransmit the packet.
No. So these are measurements that you got from the last sender act. You got these measurements from, you sent a packet and you receive an act for that packet. Now you have a time measurement for round trip time, right?
Right.
So that is, and then you have some value A, right, which was our last round trip time. And now you receive some value B, which is our new round trip time. Right, there is a measurement that we can take of the distance between these, which is the rate of change, right? And then we take 90% of this, 90% of A, times,
4 times 10% of
yeah, 4 times 10%, so 0.1 of A minus B. This is a place.
So if there's a worst case scenario whereby the rate of change, okay, say it took a longer time
Mm-hmm.
for the next act due to some network congestion, and the time it took is actually longer than the what's it called again? The timeouts. That's what I always forget.
Uh-huh.
That packet gets retransmitted.
That does, and there's no measurement taken.
That
Right.
was-
So, and I guess this is, you're absolutely correct, this is B minus A. So notice when.
And is that
when-
the absolute value of that?
Huh?
Is it the absolute value of the
No,
rate of
no,
change?
no.
To
So,
ramp down if you're.
right, because you want the number to get smaller if
Okay.
you get a packet faster. Right? So if B is bigger than A, that means it took a longer time to travel. This number is positive, right? And so now this A becomes bigger, right? If B is smaller than A, then this number is negative, right? And our measurement becomes smaller.
So in the case that was presented where like the rate of change is like really high and we don't respond fast enough and we start timing out packets, do we just start increasing our timeout value? Do we like notice, wow, I'm timing out a lot, maybe I'm not responding fast enough? Like,
Okay, so yeah,
like
so
our curve isn't actually like still not matching the network congestion.
so you have something that's super sharp, right?
Yeah.
And so you're not getting measurements because you're timing out, right? Timing out, timing out, you're not getting measurements.
Mhm.
So then,
Are we just hosed?
no, we're not hosed because it works. My guess is that they say A is something very big, like you have a default value for A, if you can't get a measurement, right? To make that thing grow quickly.
That would make sense. So that is like a fail-safe, you play it safe.
Mhm. Remember, and this is stuff that's happening on the host, so it doesn't affect the internal network, right? You might get timeout values because you have a bad cable in your house or something, right? So,
Was that 4 times 0.1, sir?
Huh?
Was that 4 times 0.1?
Yeah. So we take last known measurement, right? 90% of the last known measurement, and we want 10% of the difference between the two measurements. But that doesn't rise fast enough, so they simply shift it by 2, multiplied by 4, and then that makes it rise very quickly. Also makes it fall slower, right? Because you might rise way too much, right? But you know, as it comes down, right, it falls down quickly too. So let's take a look, just as a primer, on that topic of congestion. So we have capacity of a network, right? What we would like is, as we're adding load to the network, we would like it to look something like this. Right? Ideal. We add stuff to the network until it is full, and then we can't add anything to the network. So ideal is probably not going to happen, right? Because we need to do some averages in there, right? So maybe a better curve would look like this. Something that might be achievable. If we don't account for congestion in a network, right? So have the network aware of congestion. We don't allow the network to be aware of congestion, and we're only relying on hosts to do flow control. What do you think this graph looks like? Right? So we're going to rise, right? Flow control is taking care of both ends, right? But somewhere in there, the network gets congestion, right? Right here. Let's say this is where it happens. We start hitting congestion. What does the rest of the graph look like if we don't take care of it? Bam! Right? It tanks. Why does it tank? Huh?
Everyone's gonna slow down.
Everyone's
The
timed out.
amount of packets.
Oh, right. Because what's happening here is we're getting lost packets, right? What do the hosts do when they lose packets? They add more packets to the network, right? We hit our timeout value. We didn't get an ACK, right? We add another packet to the network. Now less people are getting ACKs, and so more people are adding more packets to the network, right? It literally crashes, and the network stops functioning.
As it recovers.
Huh?
As it recovers.
We're going to build in congestion control, and so it doesn't happen.
Okay.
Right?
Would this be like when a website goes down because too many people are ordering something? Not really.
Yeah, but that really happens at the remember we talked like a host has its own queue, right? So yeah, you can overcome a queue on a host. Like Amazon has many hosts and the things are distributed, right? So you can have a bunch of connections and a bunch of queues. In fact, does anybody know why AWS was created? It was created to handle Christmas Day, or actually the day before Christmas. So the 23rd and the 24th of December. They created all these computers because they were losing money because people couldn't order things.
The last day.
And so they made this giant cloud, and then they decided, what the hell do we do with it the rest of the year? Right? Oh, we can just sell it. We have all this extra computing space, right? So And that got him into the cloud business.
Yeah,
Huh?
because
Yeah.
what
Yeah.
happens on December 24th when I try to.
You better not be running anything important on, if you are using Elastic Cloud and you want something to run on like December 23rd, you better just not count on that.
Nice.
Pay a lot for
Brilliant.
Because let me tell you, Amazon is not going to sell you your cloud service for 2 cents an hour versus whatever that they're making some. It's pretty cheap as far as margins, but they're making lots of them, right? And they're not going to sacrifice themselves for you. Sorry. There are services now you can buy in Amazon where you get a guaranteed rate of service, which is why it is much more than 2 cents an hour or whatever, right? Because now you're cutting into Christmas time, right? They're actually renting you computers that they need, right? So you have to pay for those. All right. Also, so this is what happens to capacity and load. Also recognize that there's also a delay. Because as we're filling up the queues in the network, right, the delay is also getting. So if we had some kind of, like, I don't know, let's say, and this is percentage rate of 1 being maximum delay, right? It looks something like this. Of course, there's some point here where you die because that's the queue's filled up. But if you had an infinite queue, right, you could be infinitely delayed. So, in this particular graph, recognize that everything on this this line isn't actually throughput, right? So if we're looking here, this same graph, and we're going to look at just pure throughput, what's the graph look like? It looks like that. Right? This is useful throughput. Good put. That's actually the real name for it. It is good put. And this is throughput. Right? This is bandwidth saturation, and this is information saturation. So information saturation, right, it falls off because what happens here? We start putting duplicate packets into the network, and we're not adding any more information to the network. The network simply becomes saturated and entirely full of duplicate information because it can't be delivered anywhere.
Again, what did you say that the throughput was called? Good put?
So it's called good put.
Information
It
saturation.
actually, but good put is a point of, is information saturation,
And
right?
the other one?
So how diverse is, if we're sending new packets, then every new packet is, we'll just call that, let's say it's essentially new and nobody's sending duplicate packets incidentally, right? Every packet is new information to the network, right? Throughput is simply just a measurement of how many packets are on the network. So if we start sending duplicate packets on the network because we're not reaching, then the information richness, I guess, of the network sharply falls, right? Until everything on the network is duplicates of everything else.
Did you say that the throughput was something saturation?
So the throughput is a measure of bandwidth. It's a measure of network capacity.
Thank you.
Good put is a measurement of information. Useful information that you want to deliver one place to the other. So as always, right, we want to prevent this to happen and it becomes a bandwidth allocation problem. right? There may be more people on the network than can use it, right? So we have to divide up that bandwidth in some way such that we can do it entirely distributed. Nobody's in control. And we can be fair. So one of the ways that we could do it in our example is we could just cut off HBO on Sunday nights. You can't broadcast anymore, right? That might solve, in our simple example, our bandwidth problem, right? But that's not fair. And in the sense of fair, doesn't mean that everybody gets equal bandwidth. It means that everybody can, in fact, transmit at some speed. And we'll get into like quality of service and, right, can have really sharp arguments about fairness in the internet and so on and so forth, right? But basically that's it, right? We need to come up with a bandwidth allocation, which takes us right back to the early physical, which everybody hates, right? But this will be familiar ideas, and we'll solve bandwidth allocation problem so that everybody can transmit. That is all I have for today. So